Good morning and good afternoon for Canberra. My name is Gabriel Ignat, and I'll be presenting the Getica CCS Project Capture Feasibility Study section. I am the project manager of the Getica Romanian demonstration project, and I'll take you through a brief presentation of the overall capture feasibility study that was undertaken starting with 2010 and 2011, and a little bit of history background, if you like, about the overall location and characteristics of the power plant and so forth. So a little bit about myself. I've joined the project in May 2010, so 2 years ago, as project manager at ISPE Bucharest, Romania. I was involved from the beginning in the pre-feasibility study activities. Mainly, this was the selection of the location of the CCS project. I did coordinate the feasibility study for the integrated CCS project. And my previous experience is in oil and gas projects, both engineering and construction, mainly in the Middle East, Qatar, Abu Dhabi, basically where the major projects are. Now, I'm a power plant engineering, I got the engineering degree from the Polytechnic University in Bucharest in 2005. People might say that I'm fairly young for such projects, but I would say that the key characteristics that mainly a project manager or coordinator of CCS projects should have is a little bit of the both worlds, which is oil and gas and power plants or the energy sector, because you need some knowledge about the power plants to know how you address the integration and everything within, but you also need a little bit of oil and gas experience to be able to speak the same language with the storage section geologists and specialists. So I often had discussions, and they were amazed that I could understand what they were saying. And this, I think, it's a worldwide thing when, of course, geologists are very proud of their work, but they consider that nobody else could understand what they're doing. So basically, I think I handled very well the entire full chain, and my understanding is extended throughout the project. Now, today I'll be speaking only about the capture, and of course further information can be always consulted in the report that ISPE has prepared for the GCCSI Institute, referring to the capture plant and integration into the power plant. Now, the feasibility study results for the Getica project, the main ones, the key ones that I will approach and I will discuss a little bit about today. Now, the technology selection, we went through a process. This was the first thing that we did when we initiated the feasibility study, to select the technology. Now, depending on characteristics of the power plant, available land, the area within the power plant, the water source, the temperatures, and so forth, available utilities, all that led to the selection of the chilled ammonia process. I will not hide that more than technical was also in consideration, of course, financial also, availability of ammonia in the region versus other solvent-based technologies. And also, while the Getica project was prospecting at that time in 2010 to be a participant in the NER 300 competition for funding, we have basically reviewed the status of the CCS projects worldwide and mainly in Europe to see where we could fit the Getica project and how can we bring added value to the CCS community by doing a project that was not similar to others or would bring added value to specific areas of CCS. Now, we try to optimize the process, and of course in the feasibility study stage, there's a certain degree of optimization that you can do, and of course it will be developed in the FEED in the next stage of the project. Now we try to minimize the impact that a capture plant would have on the power plant, and this, if you like, we had two major objectives there: to lower the specific electricity consumption that is required by the capture plant, but also to reduce the steam consumption that is needed for the chemical process of washing the flue gases. The electrical department, of course, was not very pleased that we would bring some additional consumers, but also an additional generator, not the ones used already in the power plant. But what we did is we provided a back pressure turbine that this way we could lower the pressure of the steam needed for the chemical process, and also recover some of that energy in the form of electricity to be used for the internal auxiliary consumption of the capture plant itself. Now this is also related to the heat integration concept, and this will be explained a little bit in more detail further on in the presentation. But we had several concepts that we have analyzed, and mainly we had the same focus that the heat integration, which means integrating the steam and condensate into the power plant, so the exchange of those two flows would bring minimum impact in the normal operation of the power plant. Of course, everyone says that when you bring a capture plant into a power plant, you will drastically reduce its efficiency, and of course you will reduce the power outputs, meaning you will reduce the financial income of the power plant. That is true, and this is why we try to minimize the actual consumption of the capture plant. Of course, one of the main results was the operation and the construction, the investment costs, and those were estimated at a plus minus 30% for the entire CCS project. The identification of the interfaces with the power plant and also with the transportation and storage, if you like, more a conceptual scheme of the overall project. Of course, the capture plant is the one that will provide the characteristics of the CO2 stream. Transportation and the storage, nevertheless, should always present the minimum requirements that they would need to be fulfilled for the CO2 stream in order to minimize the costs, I would say, for material, for example, for transportation, for the pipeline, but also for storage. They require a minimum pressure and a minimum CO2 characteristic to be able to inject that, and that is also related to environmental aspects related to the project. And a preliminary model, a 3D model, has been done for the new power plant. This has been very useful in terms of visualizing the location of the major components of the capture plant in relation to the existing components of the power plant. The CO2 stream that will be delivered to the transport has been characterized, and the actual output of the capture plant has been, I would say, with a very high accuracy estimated at that point. Of course, the overall final objective of the feasibility study, based on all the technical and financial results, was the NER 300 application for the Getica CCS project. Now a little bit about the power plant, because this would explain very well and would present the advantages that the Turceni Power Plant presents for the CCS project and reasons why we have chosen this power plant. This was in an action that was led by the Ministry of Economy, and Turceni was based on several criteria was selected as the power plant for the first demonstration project. That doesn't mean that we are not looking for that future CCS project in the region, of course, but Turceni was given its current stage of development, and future development has been considered to be the winning hand, if you like. Now, Turceni is lignite-fired power plant, and it has a conventional steam cycle in condensation, and it operates in the base loads of the national grid. Now, the lignite is local lignite. This is very important, and it's important for the reasons that we're doing CCS in Romania, and we're doing CCS at this power plant. The lignite is a couple of kilometers. The mines, the coal mines, are actually within the same company as the power plant. So we're not talking about a single entity. When we say Turceni energy complex, which means the power plant itself and the lignite mines adjacent to the power plant. Now, it has 7 power units that were commissioned in 2 stages. Each unit is a 330 megawatt unit. The first stage was the first 4 units, number 1 to number 4, between the years 1978 and 1982. So we're looking at 30, 40 years old power plant, and the second stage, another 3 units, number 5 to number 7, between 83 and 87. Now, this is one additional thing that was unlucky for the power plant, I would say, but very lucky situation, very favorable for our CCS project, that power unit number 8 was stopped by a governmental decision in 2002. Now, this means that the initial power plant was scheduled to have 8 units, but the 8th one was never constructed. Now, the advantage that it presents for our CCS project is that we have available land within the power plant premises, and we also have available installed capacity for utilities like cooling water and so forth, because the entire design was for 8 units, but now having 7, then it creates a gap. And if you like, by doing so, by not constructing the last unit, what they actually did is they provided a CCS-ready power plant, because they had the area, the land already available, and they had utilities and so forth. So you could see this is one of the main advantages of why Turceni was chosen. Some other characteristics about each unit, you could see in which year it was commissioned. The year is between brackets, and you can see the current status, if it's in operation, or if it was decommissioned, or it will be decommissioned. So what's important is that unit number 6, to which we will apply the capture facility, is now in conservation, and they're actually moving forward with the retrofitting or rehabilitation activities. And they're prospecting to have the rehabilitation finalized by the end of 2014. That would be an early finish. If you see unit number 8, unfinished, decommissioned, available area. Now, about unit number 6 of 330 megawatt, the rehabilitation is undergoing. It does have a wet flue gas desulfurization system that is being installed and should be commissioned this year, although it will be put in conservation until the power plant is ready. But the desulfurization system is actually the output of that system is where we're going to take the flue gases for the capture plant. It also has an ash and slag dense slurry system that will also be commissioned and expected to be commissioned this year. So what we're looking at a unit that will be rehabilitated. So it will be almost brand new, if you like. It will extend its lifetime with minimum 15 years. It will have all the latest technologies in place, especially environmental technologies like desulfurization system. And this is, again, some of the advantages of the unit and why we have chosen. And in terms of schedule, 2014, while we're prospecting end of 2015 to have the capture plant commissioned, then it fits very well with our schedule and with the constraints that are coming from NER 300, let's say. Although now it has been pushed in 2016, we're prospecting to keep the 2014 December milestone. We'll look more into that during the feed stage, but for now we're looking at 2015. A little bit about the unit: 330 megawatts gross power. The 310 megawatt is the maximum long-term available gross power, and the annual average is 280 megawatt. Now, what we will do is we will install the capture facility, and it actually has been designed in the feasibility study for a 250 megawatt net output. So basically, after the auxiliary consumption of the power plant, we will treat the flue gases, which are equivalent to a 250 megawatt. And this is coming again from the NER 300. That was the minimum threshold. We did also prospect during the feasibility study ways to upscale the capture, and if by designing today for a 250, if it will be able to upscale and take the entire flue gases amount from the power plant. We did not go into too much detail, but what I can tell you today is that this is prospected as an option. Of course, the decision can only be taken after the first year of operation to see if we can take the entire flue gases from unit number 6. Of course, having an 85% capture rate, that would mean we're still going to have some CO2 in the atmosphere, but that will be less than 15% of what the unit will actually have without CCS. Moving forward, the capture technology that was chosen, the chilled ammonia process, and basically what it is that the cooled flue gases will be treated with ammonium carbonate, and it reacts with the CO2 to form the ammonium bicarbonate, which by raising the temperature, then we reverse the reaction and the CO2 is being released. Then the CO2 is compressed and shipped over to the transportation. The advantages of this technology is that it's energy efficient, high CO2 purity and high CO2 pressure. Now we're prospecting the output pressure of the capture plant to be 120 bar. We've looked also at a maximum of 140, but for, let's say, the stability or economical reasons, we say let's fix it at 120, and we're going to need a booster for storage. So if we would have raised it above 140 bar, that we would have seen a higher investment cost that would not justify the capacity of the compressor and pump in the capture plant. Now, this technology is tolerant to oxygen and flue gases impurities. It has a stable reagent towards the ammonia, and no degradation is possible on the reagent. No emission of trace contaminants, and low cost and globally available ammonia. This is another reason, and we do have in the Oltenia region where the power plant is, we do have a couple of ammonia producers. And The byproduct also has a value, so it can return part of the operation cost, and it can be a benefit. And that's the fertilizer, is the ammonium byproduct. Now, to move a little bit further, and I'm going to go quicker through this because this is a project which is already known, and it's a validation facility at Mountaineer, New Haven. And what the Getica project actually did is it benefited from the Mountaineer project's outcomes and validation to be able to improve the process itself and to reduce the energy consumption of the capture plant, the overall energy consumption. Now, a couple of things have been demonstrated in the Mountaineer facility, and the main one, I would say, would be the demonstration of the purity, minimum 99%, but the capture rate also is a very important aspect, the 90% demonstrated versus the 75% capture rate which was designed. So we're very confident that the Getica project capture plant will reach the minimum 90%, although we have a threshold of 85% today. The ammonia losses also were in line with the predictions and with the initial simulations. The energy penalty is the same. The availability of the capture plants and also the operation or the ways of coping with the power plant operation regime or modes is very high. So it's the availability being greater than 90%. It brings a lot of confidence in determining the CO2 that can be stored annually. Now, to move forward and to go a little bit into detail about the capture plant itself, the integration concept. This was the second one that we have prospected out of 6 concepts. Now, what you see with dashed lines, it's the new equipment and new installation that we will bring in the power plant, and modifications that will be done to the current scheme of the power plant. You can see on the top here that what we have is the back pressure turbine with a generator. This is the one that I've been telling you in the beginning that will bring an additional power to be used for the capture plant consumption, electricity consumption. And the steam is coming, it's a high pressure steam, and we're using this one as the main steam source. We're also using steam at between the intermediate pressure and low pressure crossover. We're taking steam out there. That with the pressure being lower, it's at the pressure needed to be included in the to be used in the capture plant. Now the condensate will also be cooled, and actually the condensate will be used to cool down the steam before it's returned into the power plant's condensate system. No contamination of the condensate is foreseen in normal operation. So if any conditioning of the condensate is needed, that will be included in the capture facility itself. A little bit about the integration into the power plant, and this is a very simple but very comprehensive interface scheme. What we have is on the left-hand side, we have the carbon capture plant. We have defined this as inside battery limit, which is strictly related to the new equipment that will be installed. What we have on the right-hand side is the power plant, so the actual existing unit. And what we have between them is what we have called the capture plant outside battery limit, OSBL, which is not strictly within the battery limit of the capture plant, but it's related to the integration with the power plant. So this is basically the interface or the integration part within the power plant. Now a little bit about the main streams between the capture plant and the power plant. First of all is the steam water cycle, and this connection is point number 1. Over here it's the steam and condensate, low pressure, high pressure steam, and the condensate that returns into the power plant. So this one is single line, but it does represent steam and condensate, going steam one way towards the capture plant and condensate returning into the power plant. We have blowdown. This is for usual blowdown of the capture plant in normal operation. Process water, number 3, the next one, and it's what we will use is actually we will need only makeup water for the capture plant. The potable water, then electrical power supply, which will be connected to the substation of the power plant, and a new substation will be within the capture plant. It has been presented at CCP substation here in OSBL for the reason of highlighting that there will be a new substation included. Now the flue gases, now this is very important. Probably this one should be number 1, because without flue gases, of course, you have no capture. But it's number 6 over here. We'll have a flue gas duct that will come from the output of the desulfurization unit, and it will go to the capture plant. I will show that on the 3D model later on. The CO2, of course, which is number 7 over here. This is actually the interface with the transportation system. So we will take the CO2 after the CO2 compressor units and the metering station of the capture plant, and we're going to take that by pipeline above ground for a couple of hundred meters within the Turceni premises. Then we're going to go underground for about 40 kilometers. Now the sewer and drainage system, this will also be part of the integration and will be integrated with the existing systems of the power plant. Demineralized water, ammonium sulfate product. This will be strictly delivered to the capture plant, so there's no interface with any existing systems of the power plant. It's just the feed of the ammonium to the capture plant. This will be done by trucks. And of course the firefighting water, which will be connected to the existing fire water loop inside the power plant. Now a little bit about the area that we have the new equipment in. You can see here on the left side, top left photo. This is a photo from the 3D model, and in the left top corner of that picture, you can see the existing cooling water tower. And what we did in the feasibility study, we prospected also to use that cooling water tower, which was initially built to be used for unit number 8 and another unit which is currently being decommissioned. So that one has never been used actually, and we did not go with retrofitting the cooling water tower due to the higher cost and lower efficiency than installing a new cooling water equipment over here and a set of chillers, which would actually be smaller and would actually be more efficient than the cooling tower itself. Now, the main equipment of the capture plant is the absorber, which is a concrete building over here. You can see the flue gas duct with purple color, which is coming from unit number 6 desulfurization plant. The flue gases will enter the first stage of the absorber, will then circulate into 2 more stages, and then it will exit the CO2, the flue gases with 85% minimum less CO2 will exit the stack on top of the absorber last stage over here. You can see it better on the bottom photo. Now what we have in addition to that, we have the columns, the regeneration columns over here next to the absorber. Then we have a set or multiple sets of heat exchangers, and we have a ammonium tank, which is right next to the heat exchangers and the columns. And now looking at the bottom photo, we have the compressor unit, compressor station, which is compressor first stage, and then the last stage is the pump, turning the CO2 into liquid. Then we have the chiller system and the cooling water system, which is a new unit. And then the buildings that you see here, the brown colored buildings, these are existing buildings in the power plant. So basically this is, in a very simple way, this is an overview of the capture plant. Right in front or next to the flue gases ducts, we have the control building, and also this is the location of the future back pressure turbine, the auxiliary turbine that will recover some of the energy from the steam taken out of the power plant. Now, to go over to the major conclusions for the feasibility study for the capture the plant. First of all, the chilled ammonia process. Now, this was selected based on the higher performances and the negligible environmental impact. Now, using ammonia in the power plant is no risk at all, because the power plant itself already uses small amounts of ammonia at this point in a different concentration, but nevertheless it does have permits to use ammonia within the power plant premises. So we foresee no problems with permitting on this one. The chilled ammonia process has been validated, and as I have shown earlier, within Alstom's research and development roadmap, and the New Haven validation facility is one of the milestones. The ammonia process has demonstrated to be robust, steady-state operation. Even, as I said, as the unit, the power unit, has different loads, the capture plant can adapt to those loads. Process simulations for the capture plant have been proved to be reliable, and the predictions have actually been met, and the parameters that were predicted as the CO2 capture rates, the ammonia losses, the energy demand of the capture plant, the solution circulation rate, and also the CO2 composition, which is important for transportation and storage, have all been demonstrated. Now, this means that from previous R&D projects of Alstom, the confidence in the design for this large-scale demonstration project is very high. And of course, currently we are preparing for the FEED to be developed, which has a targeted objective of plus or minus 10% cost estimation before we go into EPC. Now, the FEED is currently being prepared on all stages, and we do expect to have the kickoff before fourth quarter of this year. So we're going to have to move a little bit faster with the FEED. We started some preliminary activities on this, and basically we're keeping the milestones that we had for the capture plant initially. So these would be in terms of capture plant feasibility study, and in terms of lessons learned, and in terms of decisions that were taken during the project, these would be the main highlights. And as I said in the beginning, a lot more details for the technical persons or engineers that are interested in the capture feasibility study can, of course, be studied in the public capture feasibility study report that is available on Global CCS Institute's webpage. Thank you very much for this opportunity to present the project. And of course, if there are any questions, or if I can go into more detail on specific items, I'll be available for your questions.
Thank you very much, Gabriel. That's been a really good overview of the feasibility studies that you've been doing. One little question that I have is, given that you're retrofitting, or you're putting the capture plant onto Unit 6, given the other units within your plant, and also I guess the decommissioned plant, assuming all goes well, what's the view, or what's the future goals, I guess, or the future ambitions for those additional units?
Well, thank you very much for the question. That is one of the interesting aspects that we have prospected in the feasibility study. Now, what I did not mention is that the power plant is prospected to have an operation over the next years, or over midterm strategy, only 4 units still active. So that means that 3 of them will be decommissioned. By decommissioning those units, of course, this will mean that more land will be available for future CCS projects. Now, a decision, of course, cannot be taken at this point, but I can say that the power plant itself is and will be in a good position to further develop capture plant at that location in the future. If the Getica project is successful, of course, it will, first of all, it will draw a lot of attention. I'm sure of that. But second of all, will give the power plant itself and the Romanian companies and regional community, CCS community, will give the confidence to move forward into new projects. Of course, Turceni will already have the know-how to take a decision and be fully aware if they will go forward with more capture plants or not. So this is again part of the decision or strategy, long-term, mid-term, long-term strategy of the power plant. But of course, it was prospected, and a couple of items were highlighted of why we consider that more capture facilities can be installed here. Of course, Turceni is one of the power plants in the region. We have let's say at least 3 other major similar size power plants in the same region. And what we're prospecting is, and this is again long term, I would say after 2020, to start constructing capture plants in similar power plants in the region. Now, the key is that we should demonstrate the storage, and based on that, I would see no problem once the technology, the capture technology and various technologies will develop and will actually bring the cost down and will bring the efficiency up. Then it will be, when we go into commercial, it would be easier, and actually we would have the know-how at that point to take good decisions.
Okay, and presumably the additional plants and the others in the region will use the same transport and storage facilities or infrastructure.
Well, it will use the same storage because it's saline aquifer, is geological formation, so it's there, it's going nowhere, and basically if we prove it now, then the capacity that we're foreseeing for the storage, it's more than enough for the power plants existing today in the region. Now about transportation, the design, and we have some limitations. We did not over-design the transport, but at least if we have a route, we're not going to use the same pipeline, but we will be able to install a new pipeline as needed at that time. So tapping into the pipeline that we have in the Getica project will have to be discussed at a later time. But of course, yeah, it will. The barriers have already been lifted for CCS, so things would only turn easier from this point on, I would say.
Okay, well, thank you very much, Gabriel, for that wonderful overview, for that very interesting overview of your feasibility work. And thank you on behalf of the Global CCS Institute.